So here we have a problem which involves torque. We're trying to figure out the weight of a man using a scale that can only read to 250 newtons, which is less than the weight of the man. So the situation that we have here will allow us to figure out what the weight of this guy is, even though the weight of the guy is greater than 250 newtons. So this situation is definitely one that involves torque. So we're going to be focusing on this board. So here on the right side, I drew out the board for our free body diagram. And the first thing we're going to do is we're going to label all the forces that are acting on the board. So here on the left side, the board is resting on this point. So that's a normal force. So we have a normal force acting on the left. The weight of the board itself goes directly in the center. So we're told that the mass of the board is 3.4 kilograms. So the way you calculate weight is with mg. So 3.4 kilograms times 9.8 gives us 33.32 newtons. The weight of the man, which is what we're solving for, we're just going to label that W, and that'll come out in newtons. So this W is what we're looking for. We're looking for the weight of the person. And then over here on the right side, the board is resting on the scale, and that also is a normal force. You know, this scale is just a surface, but we're told that the reading of the scale is 210 newtons. So this right here would be 210. The reading on the scale is 210. So that's what this force is. This normal force is 210 newtons. The board is pushing down on the scale with a force of 210 newtons, so the scale pushes back with a force of 210 newtons. Okay, with any problem involving torque, which is a problem like this, we must have an axis. Now, the place to put the axis is the place where you have the most unknown forces. And the reason for that is forces that act directly on the axis cause no torque. The torque equation is force times lever arm, and the lever arm, D, is measured from the axis to the force. So if a force is on the axis, the D is 0, so therefore that force causes no torque. So this normal force here on the left will not appear in the summing of the torques. So we're going to put the axis on the left. Okay, so let's label the distances. Our axis is here on the left. So the distance from the axis to the weight of the man, that's 1.2 meters. The distance from the axis over to the center of the board, which is where we drew the weight of the board, that distance is 1.5 meters because the whole length of the board is 3. And then the distance from the axis over to the far side of the board is 3 meters. That's the full length of the board. And the nice thing here is that these distances are all perpendicular to the forces. They're all perpendicular to the forces. Okay, now the sign convention for torque is clockwise, counterclockwise. It really doesn't matter which way is plus and which way is minus. So with the axis being here on the left, this force, the weight of the man, is trying to rotate the board clockwise. So this is going to be a clockwise torque. This one is clockwise. And then this torque over here is counterclockwise. So let's go ahead and say that clockwise is plus. We're going to say that these are positive torques, and then counterclockwise is negative. Okay, so the answer to the first question lies in the summing of the torques. So summing the torques, starting with the weight of the man. So we have W, which is the force. And again, the torque equation is just force times lever arm. So the force for this torque is W, and the distance corresponding to it we go up like this, is this 1.2. So we have force times lever arm. Okay, plus the next torque, is the force is 33.32, that's the weight of the board, and then the corresponding distance, the lever arm, is 1.5, and those are perpendicular. Okay, minus, this is a negative torque because it's opposite the other two. We said that these two torques were positive because they were clockwise. So this torque is in the opposite direction. It's pulling the board or pushing the board counterclockwise. So minus 210. And then the corresponding distance here is 3 meters. And again, those are perpendicular. And then the sum of the torques cancel to 0. So in this equation here, the only thing missing is the weight of the man. So you can solve this for W, and we get his weight to be 483.35 newtons. Okay, now the second question can be solved with summing of forces. Let's see, I'm going to erase this dude here, make some room. We'll do it over here. Okay, so the way we're going to answer the second question is by summing the forces. So summing the forces in the y direction, we have over here, we have normal force up, which is what we're looking for. And then over here, we have plus 210 newtons. So both of those are positive because they point up. So our sign convention for summing the forces, we're just saying up is plus, down is minus. This is no longer clockwise, counterclockwise. Force just cares about, up, down, left, right. Okay, minus, okay, the weight of the man we found out was 483.35. That's what this is right here, 483.35. And then the weight of the board, minus 33.32 newtons. The sum of the forces equals ma, but there is no acceleration. That equals 0. So we can just set this equal to, just put this in as 0. So from this equation, the only thing missing is the normal force, which comes out as 306.67. And that is the normal force acting on the left side of the board. So the idea is that the total up force, we have two forces that point up. These two forces added together must be equal to the two down forces added together.